All right, our next speaker is Satoshi Kura. They are talking to us about verifying properties of probabilistic programs, and in particular, computing bounds.
Okay, can you hear me? All right, thank you for the introduction. Okay, can you hear me? Right, sorry. So this talk is about the quantitative verification of probabilistic programs. So many properties of probabilistic programs are quantitative in nature, and for example, the termination probability is real number between 0 and 1, and also the expected runtime is a non-negative real number or infinite. So there are many such quantitative properties, and our goal is to verify lower bounds of such quantitative properties. And it is known that many of these quantitative properties can be characterized as least fixed points. So here, K is a monotone function that is induced by a predicate transformer. And in this talk, I will often represent the least fixed point as the least solution of a fixed point equation. Okay, so here's an example. So consider a biased random walk, which is biased toward the origin, and in this case, the expected runtime is given as the least solution of this equation. And here you can see that the right-hand side of this equation has a similar structure as the loop body of this program, and in general we can easily define a translation, inductively define a translation from a given program to such a fixed point equation. And verifying upper bound is relatively straightforward, and this is because by the Nastatarski theorem, to give an upper bound of the least fixed point, it suffices to find a prefixed point of K. One advantage of this approach is its generality, and so this theorem applies uniformly to any property that can be characterized as a least fixed point. On the other hand, verifying a lower bound is much more challenging, and so one naive approach to verify lower bound is to apply a clean iteration like this, but this may require a large number of iteration, and in general, there's little hope of obtaining the exact value with infinitely many steps. And several alternative approaches have been proposed, but they are typically tailored to specific properties and do not apply uniformly because they do not directly exploit the least fixed point characterization. So in this work, we address this issue, and we propose a new reasoning principle for reasoning about lower bounds of least fixed point. So our main theorem is shown here, but you don't have to understand it now. So I will explain this in the next several slides. But based on this theorem, we also implemented an automated verification tool that automatically applies this main theorem to concrete problems. Okay, so now let me explain the main ideas behind our theorem. So the first key observation is that verifying lower bound become much easier if fixed points are unique. So recall that by the dual of the Naster-Tarski theorem, any post-fixed point gives a lower bound of the greatest fixed point. So if the least and greatest fixed point coincide, then any post-fixed point also gives a lower bound of the least fixed point. So then the question is, how can we guarantee the uniqueness of fixed points? So let's first consider the special case where k is bounded by 1. In this case, it is known that almost sure termination guarantees the uniqueness of fixed point. Intuitively, the gap between the greatest and least fixed point corresponds to the contribution of non-terminating execution passes. So, if the program is almost surely terminating, then this gap vanishes and the two fixed points coincide. And moreover, almost sure termination can be witnessed by ranking supermartingales. So therefore, the existence of a ranking supermartingale guarantees the uniqueness of a fixed point. And it is straightforward to extend this result to the case where k is bounded by a constant m. However, this generalization is not enough because, for example, in the random walk example that I showed earlier, the expected runtime cannot be bounded by any constant. So this generalization cannot capture such cases. So to handle such cases, we consider a more general setting where k is bounded by a function u. In this case, restricting the domain of k is always possible, but on the other hand, restricting the codomain of k is only possible when u satisfies this condition. So so we assume that u is a prefixed point of k. So, but in this setting, almost sure termination is no longer sufficient for guaranteeing the uniqueness of fixed point. So we consider a generalization of a ranking supermartingale. So this is the key idea of this work. So to guarantee the uniqueness of fixed point, we introduced the notion of U-ranking supermartingale. So recall that a ranking supermartingale is a function R that decreases by at least 1 in expectation. So we generalize this definition by to generalize this definition, we reformulate the definition by reformulating the ranking condition using the function k, and also we replace the constant decrease of by 1 with the upper bound function u. So we define the resulting notion. So we call the resulting notion a U-ranking supermartingale. And we showed that the existence of a U-ranking supermartingale guarantees the uniqueness of a fixed point of k bounded by U. So then, once the uniqueness is established, then we can combine it with the Naster-Tarski theorem to obtain a lower bound. So this is the key idea of our main theorem, and the statement of our main theorem brings these ingredients together. So so in our theorem we have four conditions, and the first condition ensures that k can be restricted by u, and the second condition states that R is a U-ranking supermartingale, and the third condition requires that L is a post-fixed point, and the last condition ensures that L is in the restricted domain of K. So under this condition, we can conclude that L is a lower bound of the least fixed point. Okay, so as an example, let's apply our main theorem to this random walk example. In this case, we can choose the functions u, r, and l as shown here. Then it is straightforward to check that the four conditions of our main theorem are satisfied by these functions. Then, by our main theorem, we can conclude that 3x is a lower bound of the least fixed point. And in fact, this is the exact lower bound of the expected runtime. I would like to emphasize that the assumptions of our main theorem is general enough. We assume that k is omega continuous, omega co-continuous, and affine. But typically, predicate transformers typically satisfy. Predicate transformers typically satisfy the condition of omega continuity and omega co-continuity, and moreover, predicate transformers for probabilistic programs usually satisfy the condition of affineness. And as a consequence, these assumptions are satisfied by all these quantitative properties shown here. And also, we can obtain a stronger result by slightly extending our main theorem. So here, suppose that we have a function k prime that under-approximates k. Then, obviously, the least fixed point of k prime is also under-approximates the least fixed point of k. So, if we apply our main theorem to k prime, then the resulting lower bound is also a lower. The resulting lower bound is also a lower bound of the least fixed point of k. So this extension is quite simple, but it certainly increases the power of our main theorem. And specifically, it enables us to simulate several existing techniques for lower bound verification, including guard strengthening, stochastic invariance, and gamma scaling. Okay, so finally, I will explain our implementation and experiment. So we implemented an automated verifier, a mu-val QFL, that automatically applies our main theorem. So our tool solves a bound checking problem rather than a bound inference problem. So its input consists not only of a least fixed point equation, but also of candidate lower bound. The goal here is to determine whether the given candidate is indeed a valid lower bound for the least fixed point. So our tool, mu-val QFL, is based on template-based synthesis. So specifically, our tool uses piecewise polynomial template where the partitioning of the template is determined by the branching structure of the input equation. Then our tool generates polynomial constraints and passes them to an off-the-shelf constraint solver called preexpectation. We evaluated our implementation on benchmarks taken from the literature and together with some additional benchmarks. And we use several configurations with different degrees of template, and some configuration enables the under-approximation technique using K-prime. And this table shows the benchmarks checked against the exact values. And this table shows that our tool successfully solved all of these benchmarks. And here's another table which shows the result for benchmarks that are checked against approximate values. These benchmarks were more difficult and required an appropriate choice of configurations and more time. And improving this result may require improvements to underlying constraint solver and more sophisticated constraint generation techniques. And also, our current implementation has a limitation that it only supports polynomial templates. So extending this to other template is left for future work. Okay, so this is the summary. So we proposed a new reasoning principle for lower bound verification based on the idea of U-ranking supermartingale. And our implementation is available if you scan this QR code. So thank you for your attention.
Okay, thank you. We have time for a question or two.
Hi, thank you for a very nice talk, and this is really cool work. I have a question about the condition for the uniqueness of fixed point. So what you provide is a sufficient condition. Do you know if it's also necessary?
So I don't think so. It's just a sufficient condition.
Do you have a counterexample, or?
We currently don't have, but we don't think these are sufficient.
Okay. Very cool work. Thank you.
Thank you.
Anyone else? Yep. Behind you, there's the microphone. Right behind you.
Yeah, thanks a lot. Honestly, this is something we've been waiting for quite some time. Very cool. Could you please go to slide 15? So I was wondering, do you think there is any hope to weaken that equality of K and the convex combinations you have there to an inequality?
You mean this one?
Yeah, exactly.
Well, yeah. Sorry, I don't remember, but probably, yeah. If I remember correctly, this, yeah, we need exact equality and not inequality. So.
I think if you could weaken it, that might be cool, because I believe this equality breaks for programs that are both non-deterministic and probabilistic, like in Hailey's talk. And if it's only an inequality, your rule might be like generalizable also to these programs. Would be cool.
Yeah, that's an interesting point.
Okay,
yeah,
thank you.
Great. So we already have the next paper that you're going to write based on this idea. Great. Okay, let's thank our speaker one last time. And our next speaker, please come up to the stage.